Let's talk some more about closed sets. That's what we were talking about last time. If you recall, a closed set means the complement is open, right? So, a closed set is one whose complement is open. That's the definition of closed. Closed and open are not opposites, but in terms of sets, a closed set is the complement of an open set. So in that sense, they're kind of opposite, but they are complementary, if you will. A closed set is one whose complement is open. Some quick and easy facts about closed sets, general facts. Hashtag facts about closed sets. Simple fact, one is that empty set and the entire space X are always closed. I'm not just talking about in R. I mean in any topological space, the empty set and the entire space X are automatically closed. Why is that? Remember, closed means the complement is open. This is because, here's a little proof, I suppose, since the complements, these are complements of X and empty set, right? The empty set is the complement of the entire space, and the entire space is the complement of the empty set. Which are open, right? The empty set and X are complements of X and the empty set in that respectively. And X and the empty set are automatically open in any topological space. And so their complements are automatically closed in any topological space. All right. That's the first sort of hashtag facts. I got two more facts that I'm not going to explain in total detail, but it's not so hard. You could do the proofs of these yourself if you want to in just a moment. The first one is that any intersection of closed sets is closed. This is because a closed set is a complement of an open set. And when you take an intersection of closed sets, if you take the complement of the intersection, it's the same as the union of the complements. This was the De Morgan's rule, and we talked about this in the first week of class, I think, how taking the complement sort of turns a union into an intersection. And so when you have a bunch of closed sets, their complements are open, and so the intersection of those closed sets, its complement will be a union of open sets, which is still open, which means the complement intersection is still open, which means the intersection is closed. I don't know if you can follow all those words in your head, but this, if you try to write down the proof, is straightforward. And similarly about unions, but it has to be finite this time. Any finite union of closed is closed. All right. So this is like the rules for just defining what a topology is, but the finiteness is in the other spot. So in any topology, any union of open sets is open, and any finite intersection of open sets is open. The same is true for closed sets, but you have to put the finiteness in the other place. So it is true that any intersection of closed sets is closed, and any finite union of closed sets is closed. This can be a little confusing to remember which one gets the finite. For open sets, the union gets the for open sets, the intersection gets the finite. For closed sets, the union gets the finite. All right. One more fact about closed sets, which is interesting to talk about, and actually this fact we're going to elaborate on quite a bit. In R, any single point by itself is a closed set. Right? A set of just a single point is a closed set. In R, how would you explain that? In R, I would say because a set of a single point by itself, its only possible limit point would be that same point. Like one point by itself can't approach any other point, so its only limit point is itself. And since that point is already part of the set, it includes all of its limit points, and so a single point set is closed in R. Another way to think about that in R is the complement of a single point is all of R, take away that point, which you can write as a union of two open intervals, and so it is open. But anyway, in R, any single point is a closed set. That fact actually is not always true in any topological space. So I will say this is not always true in a topological space. For example, actually we saw an example of this last time, although I didn't remark on it at the time. So the last time we had an example where X was the set A, B, C, D. I don't know, if you still have your notes from last time, you can probably just turn back one page and see this example. And it had a certain topology that where I just wrote out a bunch of stuff. All right, this was a sort of made-up abstract example. But if you look carefully at that example, I don't really care about the details anymore. But I'm just trying to demonstrate it really is possible that a single point might fail to be closed. So when we looked at that example, the closed sets included. So in that example, the set A by itself was closed, but the other ones, B, C, and D by themselves, were not closed. They also were not open, but they were not closed. All right, so that's an example of a topological space in which points of single elements are not closed. This is a little weird because, like I said, we typically would like to think of a single point by itself. It doesn't really approach any other limit points, although in a general topological space that is not necessarily the case. All right. But this property that I'm talking about, that every single point is a closed set, that actually is true in a very sort of nice category of spaces that we're going to be talking about. I will just say it here. A single point set is closed in a certain nice type of topological space, which we are going to talk about today. And that is called, this is named after a person, and it's kind of a cool, I always thought this was a cool name. This is called a Hausdorff space. A Hausdorff space is a special kind of topological space which has basically one extra property. You know, a topological space has the finite intersections and the unions property. There's one other property that you add to it that makes it what we call a Hausdorff space. Hausdorff is a person's name. It's a little bit, I mean, it's the details of the extra property have nothing to do with it, but it's kind of like an abelian group. You know, an abelian group means that it's a group, but it also has a commutativity property, which, like, to prove most theorems in group theory, you don't need the commutative property, which is why it's not required of all groups. But certain theorems, you do need to use the commutativity, and so that theorem is only true in abelian groups. And you think of an abelian group as like a special, nice kind of group. It's like it's a group, but it has this one extra property which lets you prove extra stuff. And Hausdorff topological space is the same way. So a Hausdorff space is a topological space which has one extra property, and I will tell you, here's the definition of a Hausdorff space. And the one extra property is very reasonable, and it actually, there's a simple little picture you can draw that represents the Hausdorff property. So a topological space X is called a Hausdorff space. Hausdorff space. If here it is. So it looks a little abstract, but actually, like I said, there's a picture that goes along with it. which is very easy to understand. So I will write the abstract version first. For all x, y, and x, there exist neighborhoods u and v with x in u, y in v, and u intersect v is empty. That is the Hausdorff space property. This is sometimes referred to as the separation axiom, for reasons which will become clear when I try and look at what that looks like on a picture. But this is the extra property which is true in a Hausdorff space. So it has the original topology properties, the three axioms for topology, and plus this extra Hausdorff separation axiom. And what this looks like in a picture is very reasonable looking. It says if you have any 2 points, call them x and y, then there are two neighborhoods, u and v, where x is part of u and y is part of v, and those two neighborhoods, their intersection is empty. That is, they have no overlap between them. So it means if you have 2 points in the space, you can make a neighborhood around each one. Like here's the u, and here's the v. And the u and the v don't overlap, all right? This is called the separation axiom because, on the picture, it means if you have 2 different points, then those 2 points can be separated apart by neighborhoods. All right, there's a neighborhood around this point which excludes that one, and a neighborhood around this point which excludes that one. It doesn't even, the 2 neighborhoods don't touch each other at all. All right, this is the extra property which is true in a Hausdorff space. So in words, I would say any 2 points can be separated. That's why this is referred to as a separation axiom, separated by open sets. All right. Here's a fun fact. I actually never. I've been doing topology as my research area for my whole career. Like I first learned about Hausdorff spaces, when I was in college 20 years ago. But I never heard this. Our book says it's easy to remember this word Hausdorff because it means any 2 points can be separated by open sets. They say also you can think of it as the 2 points are housed off. You get it? They are housed off from each other. My mind is blown here. I have always just remembered the name Hausdorff, which I think sounds cool anyway. I just remember what Hausdorff means. It means the 2 points can be housed off. It was really thinking about that when he named himself Hausdorff. All right. So this is the Hausdorff property. Most typical classical theorems in point set topology are theorems about any topological space, but actually many of the important theorems are only true in a Hausdorff topological space with this extra one property. I thought maybe I'd tell you a little bit about the man, the legend Hausdorff. He was a German mathematician who lived 1868 to 1942. Seeing a German death date of 1942 is a signal that this is a bit of a tragic story. Hausdorff, the end of his life, maybe most of his life, was a bit of a sad story. But one of the first mathematicians to really sort of do set theory as a career. Set theory was kind of turned into a real thing by Cantor at the end of the 1800s. Cantor was the first person to demonstrate that there were different sizes of infinite sets, the countable versus uncountable thing. That was all Cantor's work. And Hausdorff was kind of the second generation of that, right? He learned set theory from the greats and kept on carrying on with set theory. And set theory, Hausdorff was one of the first people to try to do topology using axioms. So he basically created a set of axioms for topology that would be like recognizable to us. Although he didn't do it in the same way. We typically define a topological space as a set, a big set together with a description of what are the open sets. Hausdorff didn't think of it in terms of open sets, but he thought of it in terms of what we would now call a basis for topology. But it's the same thing. So Hausdorff came up with that kind of the basis intersections property about when you have two open sets which intersect, and there is another open set which is inside the intersection of the two open sets. So Hausdorff thought a lot about his view of topology was very much based on neighborhoods and how they intersect, which is why this is a very natural thing for Hausdorff to consider as part of his axioms, because it's all about neighborhoods and how they intersect. So anyway, Hausdorff created a set of axioms for topology, and Hausdorff included this separation as part of his deal. And it was later on that people realized actually you don't need that separation axiom all the time, and it works better if you sort of describe that as a special case. But anyway, he was one of the first people to try to think of this topology in terms of axioms. And Hausdorff was Jewish, had a successful academic career in Germany, although he was sort of, as Hausdorff's life went on, it became harder and harder to live a normal life in Germany as a Jewish person. He tried to come to the United States as to NYU, I believe, as an academic, but he wasn't able to do that, and he ended up dying by suicide with his wife when they found out that they were about to be sent to concentration camps. So a sad end of the story for Hausdorff. But Hausdorff did lots of important work, and has there are several things named after him now. So he's definitely fondly remembered. If you went to the colloquium talk a few days ago about fractals, she was talking most of the time about something called the Hausdorff dimension of a fractal, and also the Hausdorff measure of a set. So those are other things named after Hausdorff. Big towering figure whose name kind of sounds like housed off. All right. So what kinds of topological spaces are Hausdorff? One is, Rn is Hausdorff, the standard topology. I hope you agree. If I let's just imagine R2, for example. If I start with 2 points, is it possible to make a neighborhood around each of those points that separates them? And the answer is yes. You can, no matter how close the points are to begin with, you can always find a small neighborhood around the one, which excludes, or it's a neighborhood around the one and a neighborhood around the other, so that those 2 points, those two neighborhoods are just disjoint. All right, so any points can be separated by neighborhoods. Right. This is true also for R1 even. R1 would look like this. Here's X and Y, where the neighborhoods this time would look like open intervals. Is it possible to put an open interval around each one so that the two intervals don't overlap? The answer is yes. You can just make, some small interval over here, some small interval over here, and they do not have to overlap. All right. So this is why it was natural for Hausdorff to include this as like a basic property in topology, because it is a basic property in Rn. We now don't consider it to be a basic property of all topological spaces. Even more than just the standard topology, how about R with the lower limit? Remember that one? This is the one in which the intervals you use for the basis neighborhoods are intervals which include the left endpoint but not the right endpoint. So can we still separate 2 points using neighborhoods if the neighborhoods you draw, they must include their left endpoint but not their right endpoint? Is it possible to separate the 2 points, x and y, by neighborhoods using those kinds of neighborhoods? Anybody got a feeling? Show me the thumbs. Can you do it? Can you not do it? I can see some of you. I see a thumb. The answer is yes, you can do it. I mean, if you make them small enough, then the 2 neighborhoods, it doesn't matter if you include the endpoints or not, right? So this x, you could make that neighborhood around it, and same with the y. It doesn't really matter if you want to use the lower endpoints or the upper endpoints or whatever. So this one still is Hausdorff. All right. How about the discrete topology? The discrete topology, remember, is the one in which every set is automatically open. All right. You could do discrete topology on R, but actually we can talk about the discrete topology on any set. Is it Hausdorff or not? So if I take, if we have x and y in some space with discrete topology, actually it is Hausdorff. You can find an open set around x and an open set around y, so that the 2 sets are not the same or don't overlap each other. So x and y, of course, they should be different, right? X is not the same point as y. Did I mention that in the definition? That is definitely important. Yeah, obviously if x and y are the same point, then this is never possible. So I should have said, can I just add this in parenthetically? Sorry about this. How about this? I will erase the comma here and change it to a not equal. It doesn't make any sense. If you allow the 2 points to be the same, then nothing ever satisfies that property. But they have to be 2 different points. Sorry about that. If I have 2 different points in the discrete topology, we can take u equal, v equal. You have to tell me 2 sets. They have to be open sets, but in the discrete topology, every set is open. So really, it could be any set. You just have to think about some set. The u includes x, the v includes y, but they don't have any other points in common. Anybody have an idea of how you could do this? The answer is kind of deceptively stupid. You want to choose an open set which includes x here and an open set which includes y here, but they have no intersection. They have to be open sets in the discrete topology. In the spirit of it's going to be kind of stupid, anybody want to suggest to me what's a stupid choice for a set which contains x for you?
You can do just x.
Just the point x, yes. He turned on his camera just to give me the stupid answer. Yeah, that's great. You can do just the point x. That's kind of the stupidest set which includes x at all. Now, ordinarily, this would not count as a neighborhood because that's not typically an open set. But I'm talking about the discrete topology, and everything in the discrete topology counts as an open set. And so that actually is a legal choice for the neighborhood. And what about the v? I'm going to choose just the point y. All right. And now those are 2 neighborhoods which have no intersection because x and y are not the same point. And so I'll say, so u is a neighborhood of x, v is a neighborhood of y, and u intersect v is empty. So the conclusion is the discrete topology doesn't matter what the space is. If you're using the discrete topology, is Hausdorff. All right. Hausdorff just means any 2 points can be separated. They can be housed off by neighborhoods. How about an example of something which is not Hausdorff? That would be R what our book writes like this. R with the finite complement topology. This is not Hausdorff. That's because, so I consider R the real line, and I have my 2 points, x and y, all right? It turns out in the finite complement topology, you cannot separate x and y using disjoint neighborhoods. It's because, I mean, the way you would do it in the standard topology is this little interval and this little interval, but those are not actually open sets in the finite complement topology because the complement of this little open interval is all these numbers out here, and that's not finite. And so those don't count. You can't use those as open sets in the finite complement. What does an open set actually look like? An open set containing x, a neighborhood of x, is a set which basically includes everything except for omits, you know, a few points here and there. Only finitely many points. Right? So this is what a typical neighborhood of x looks like. Now, I sort of chose these excluded points at random, but it has to include everything except for finitely many individual points that you're excluding. Now, I was able to exclude y, so this neighborhood of x does not include y, and I can also make a neighborhood of y which does not include x, right? That would have to include everything here, but, you know, omits a few points, and maybe I'll omit x itself. So this is a neighborhood of y. So the neighborhood of x does exclude y, and the neighborhood of y does exclude x, but that's not what it means to satisfy the Hausdorff property. These two neighborhoods have to have no intersection, no overlap at all, and that's definitely not true here. These two sets have a whole lot of points in common. Their intersection is infinite, right? Their intersection would be all the points which exclude just these exclusions, but still includes many other things. All right. So these two neighborhoods. Can I just say it this way? Any two open sets in RFC will have many points in common. Because any two different open sets, all they are is just all of our take away a few points. And so any two different open sets will still be mostly the same. They just omit a few points here and there, but mostly they're the same. Any two open sets will have many points in common. So the Hausdorff property, this thing, is impossible. Right? And so that's why the finite complement topology on R is not that is not a Hausdorff space. All right. Generally speaking, when I think about the concept of Hausdorff, I mean, I remember that little picture, but generally, Hausdorff spaces are nice. By nice, I mean kind of similar to Rn. And non-Hausdorff are weird, meaning not like Rn. You know, this is at least my own point of view. Like the research that I do, everything I ever talk about is always a Hausdorff space, just because the non-Hausdorff spaces, they look so different from Rn that, I mean, they are of interest to some people, but to me, the type of topology that I do is not always about Rn, but it's about things which look more or less like Rn. And a non-Hausdorff space is actually quite different from Rn. No offense out there to the people who specialize in non-Hausdorff space topology, but I'm not. I don't do that much, and to me it seems weird. All right. Anyway, I got onto I got onto all of this because I was talking about single point sets, and are they closed or not? It is a theorem, so I'll write this as a theorem. And actually, the theorem is quite easy to prove. There are some theorems in point set topology where the proof is just kind of, the proof writes itself almost. The theorem is that if X is Hausdorff, then and I have a single point, I'll say, and X is in the set X, then the set X is closed. All right. This is a nice property that you feel like ought to be true all the time. Actually, it's not technically true all the time. It needs the Hausdorff property or something like it. If X is Hausdorff and we have a point, then that point as a set by itself is closed. All right, let's see if we can do this. This is I think this would be a nice proof to put on our test or something, because like I said, as long as you understand the definitions of everything, each step of the proof kind of directly follows from what you said before. So I am going to assume that X is Hausdorff. I need to show that the set of just X is closed. How do you show something is closed? Well, what closed means is the complement is open. So I'm going to start by saying we'll show that X minus the point X is open, right? That's what closed means. Complement is open. So to show some set is closed, you must show the complement is open. And what is the typical way to show something is open? The typical way to show something is open is you choose a point in there, and then you have to show that that point has a neighborhood, which is also part of your set, which you're trying to show is open. So we'll show this is open. The way to do that is I take Y as an element of this, and we have to find a neighborhood around Y. We'll find a neighborhood. Let's call my neighborhood U around Y, such that, and what's supposed to be true is that U is a subset of X minus the single point. All right. So this is how you always show, well, not always, but this is the typical way to show that a set is open. You choose a point in that set and then find a neighborhood around that point, which is still in the set. All right. Now here, can I just rephrase what this stuff means? I said take Y in X minus X. Another way of saying that, rather than this somewhat complicated thing, I'm saying Y is in the complement of the set X. All this means is just Y is any point except X, right? That's what this means. This is the set of all points except X. So this just means Y is not X. So really, if I were to rephrase what I just said in there, we have, maybe I'll just say Y is not equal to X, and we want U. Can I write this? This thing here means U is a subset of X minus X. That just means that X is not part of U. Like U is a bunch of points, but none of them are X. So this means we want a neighborhood U with Y is in U, like U is a neighborhood of Y, and X is not in U, right? Okay. How do we find such a neighborhood? There isn't typically a good way to just cook up a neighborhood out of nowhere, but we have to, at some point, of course, use the Hausdorff property, that separation axiom. And I think now is a good time, right? We have two different points, Y and X. So because of it's a Hausdorff space, there is a neighborhood around X and a neighborhood around Y, which separates the two things. And actually, you can see that's exactly what we need to show here, that X is not in. We have a neighborhood around Y, and X is not in there. And that's what the Hausdorff axiom will show. So remember, the picture of the Hausdorff thing is this, right? And you can make a neighborhood around here, and you can make a neighborhood around here. So I'm going to say, that's just my little sidebar picture there. Since the space is Hausdorff. We can find two neighborhoods. Now, usually I call the one U that's around X and the one V that's around Y. I'm going to call it the other way around just because I want this neighborhood up here, U, to be the one which includes Y. So I'll say there exists UV with Y is in U, X is in V, and U intersect V is empty. But the fact that U intersect V is empty and X, so on my picture here, that's U and that's V, all right? So that means that X is not part of U. That's because X is in V, and V has no elements in common with U. Since X is in V and U intersect V is empty. All right, and this is what we said we wanted to show, right? I said we needed to show this thing in the red box there, and this is what we've got. So Y is in U, and X is not in U. Shoon. That's what we wanted. Sorry, I'm off the bottom. We wanted a neighborhood U where Y is in U and X is not in U. The Hausdorff property gets it done. All right. Any thoughts about that or questions about that? Hausdorff. There's some nice topological spaces that are Hausdorff. There's some nice ones that aren't Hausdorff, but for me, I'm a little more comfortable with the Hausdorffs. All right. Great. We got a little over 10 minutes left. I think that's enough to just briefly talk about the next thing. So we've been talking about closed sets with a little digression into Hausdorff spaces. Let's talk about a traditional sort of operation that you learned in real analysis for sets called the closure. The closure of a set. Maybe just for today, we will try to refresh our memory about what exactly does the closure mean from real analysis. I hope you talked about the closure in your analysis class. The closure is what happens. It's an operation. It's when you enlarge the set. You start with an original set, and then you create a new set, which is the closure of what you started with. The closure is when you make the set bigger. You add some points into the set to make it closed. That's the idea behind the closure. And we write it as like A bar. If the set A is just, if you start with some set A, the bar means the closure. So A bar is the closure of A. All right. I read a joke. Two topologists are going to a bar, but they had to go home because it was closed. It works better if you say a bar, like when it's written down on a piece of paper. A bar, you get it? Because it's closed. Yeah. Anyway, the closure. So in R, this is what you're already familiar with, I think. If you start with, for instance, an open interval. What is the closure of an open interval? It means you add a couple extra points in just to turn it into a closed set. So that would be written this way. The open interval bar is, well, the closed interval. If you want to make the open interval closed by adding some stuff in, all you got to do is add in the two endpoints. Now, of course, you could make the set much bigger to make it closed in some other way, but actually the closure means you sort of do it in the smallest way possible. You add as few points as possible to make it into a closed set. And for an open interval, all you got to do is add the two endpoints to make it closed. There are you can do some weirder examples though. For example, if I start with the set of 1 over n, this is like, if here's 0, here's 1. These would be the numbers 1, and then a half, and then a third, and then a fourth, and then a fifth. So the numbers go like this, right? What's the closure of that set? First of all, that set is not closed because it is missing one of its limit points. Those points, they approach 0, but that 0 is not part of that set. 0 is a limit point, but it's not in that set. I'm trying to use the language of real analysis. Of course, in topology, we don't always talk about it in terms of limit points. But anyway, what's the closure of that? You just think about, are there any points I need to add in order to get all the limit points? And the answer is you have to add in that point 0. So the closure of this set 1 over n is, first of all, you start with everything you had to begin with, which is all those points. And then also you get 0. So you have to write it this way. All the points you started with, and also you must include 0 to make it closed. All right. How about just 2 more quick examples? Q. Q is all rational numbers, right? What is Q bar? Q is not a closed set because the rational numbers are dense in R and they approach, actually any real number can be a limit point of the set of rationals. Anybody want to say? Somebody want to shout it out? What's the closure of Q? Think about it. You got to add in all the limit points.
The union of Q and the rational numbers.
Q is the rational. Did you say irrationals?
Yeah.
Yeah, you take Q, but you also throw in the irrationals also. Yeah, there's a cuter way to write that. I'm actually not going to write that as a union.
Q and the union of the reals.
Yeah, or how about, would you believe me? Just the reals, right? Q is already part of Q union R. So yeah, R is the set of this is the closure of Q. So Q by itself is missing many limit points, all the irrationals. So you got to throw all of those in, but by the time you throw those in, you just end up with everything, which is R. All right, great. And I had just one more simple example. What if I start with a closed interval and take the closure of that? The answer is still just the closed interval. This is a basic property of the closure, that if you do the closure of the closure, you don't get anything else. The closure, in fact, the closure, if the set you begin with is a closed set, then you're not going to get any more stuff by taking the closure. You just end up with that same set. So basic facts about the closure. So we always have A is always a subset of A closure. That is to say, the closure is always obtained by adding some extra stuff into the set. So you always have the original stuff that used to be there plus some extra stuff. And A bar is closed. That's the whole point of the closure. I'm trying to get us to coming up with something which we can use as a definition in a general topological space. You have to make a definition for this without using the word limit point, which is a little tricky. We have to think about what exactly are we looking for here. First of all, we're looking for something which is bigger than the original set and it's closed. And it can't be just any closed set which is bigger, because there might be many different choices. Really, you want the smallest one. This is what I said up here. If I start with an open interval, there are a lot of closed sets which include that open interval, but I want the one which is the smallest possible. So we want A bar to be, in some sense, the smallest closed set containing A. Right? Now, smallest is sometimes tricky to make sense of. What exactly do I mean by smallest? I mean smallest in terms of as a set. Actually, the appropriate way to say this, or the most convenient way in terms of making a definition in our setting, the smallest closed set. Remember that I said earlier today, any intersection of closed sets is still a closed set. So rather than saying the smallest closed set, I could just consider the intersection of all the closed sets. So I'm taking only the things which are in every closed set that contains A. That would make it like the smallest if you take every single closed set and intersect them all. Take the intersection of all of them. The intersection of all closed sets. this is going to give you the smallest possible closed set, because the intersection, of course, every time you intersect two things, the result gets smaller, perhaps, or stays the same. So if you intersect every possible closed set, this will give you the smallest theoretical closed set. So this is what the definition looks like. And maybe I'll just leave it at this for today, and then we'll talk about many examples of this next time. So the definition says, in a topological space X, I have a subset like that, then the closure of A written A bar is defined as the intersection, the intersection of all closed sets containing A. All right. This is the definition of closure. The intersection of all closed sets containing A. This can be a bit of a pain to work with, but this is the closure of a set in a topological space. All right. And I think that's going to do it for today, if that's all right.